Yes, yes, yes. Okay. Good morning. Is it okay for you guys to start now? Sure. Okay. Yeah. Thank you. Thank you very much. And thanks for the opportunity also. So guys, my video, my presentation is visible now. Hello.
Yes, sir, it is visible.
Okay. Yeah, the today's session is the application of CAE in automotive industry. So the next 1 hour we are going to talk about these applications in automotive industry. So the content of the today's discussion is the content will be, since your workshop related on the FEA, so would like to touch few topics about the CAE introduction and major applications in automotive and what are the software we are using and what is automotive safety and what are the safety systems are there and what are the crash worthiness is there and different types of the crash test and the crash regulations and the dummy evaluations and the hybrid tar and the thumbs. So these are the topics today we are going to discuss. Yeah, first we'll start about with the CAE introduction. So CAE is computer-based technique that calculates how the components or products are likely to perform in real-life applications. Basically, in our conventional method, first we'll make the design. So as per the design, we'll go for the prototype. Then from the prototype, we go for testing. Then we will check whether the component or the product is getting passed or not. In case if the product is getting failed, so again we need to do the same process. So it will take long time and we need to spend more money also. So to avoid that one, so CAE is very useful for us. So it will help us to predict the potential design issues and minimize the risk of the product. So based on that, so we can launch the product very quickly in the market. And the next day's topic is the major CAE applications. So now we are going to talk about only the structural, not talking about anything thermal. So we'll talk only about the structural in automotive. So basically we have three different domains here. So first is that strength and durability. So here, we based on that our linear simulation and non-linear simulation, we'll be calculating what is the life cycle of the part or product. So and based on that, so by using a stress approach or strain approach, we will calculate what is whether it comes under high cycle fatigue or low cycle fatigues. And at the end of the simulation, we can predict that okay, this product or this component will withstand this many cycles. The next part is that NVH, noise, vibration, and hazardness. So here, so mostly we will be doing that model analysis. So based on that, so again we go perform the harmonic simulation and spectrum analysis, random vibration analysis. So based on the analysis, we'll be getting the response as a displacement or stress or some strain, or we'll be getting the amplitude also. So based on that, we can calculate that cumulative damage also. So it also to helpful us to predict the structure, how it will behave for the particular frequency range or particular vibration level or time domain. So next one is the crashworthiness. So the crashworthiness will go in detail in next slides. And what are the softwares we are using in automotive industry? So majorly here in our company, we are using Hypermesh, ANSYS, and Primer. These things are we are using for the pre-processing. So once we get the CAD model from the CAD team, so we'll be using ANSYS Hypermesh to make the finite element modeling. In that, after the finite element modeling, so we need to assign what is the property, whether it is a beam or shell or solid. Then we need to apply the boundary conditions. Then we need to apply the loads. So these all the things will be done in Hypermesh, ANSYS, and Primer. After completing this one, so from this is sorry. So page number 3 I am showing right now here for me. Okay. Now it's moving or hello? What's moving? Just a moment. Stop staring. So now it's able to see the screen in page 3. Again, sorry. Yeah, I shared a word. Okay. Share your entire screen. Okay, now you're able to see page number 3. Okay, sorry. Yeah, sorry. Okay, yeah, so we are talking about that major CAE softwares in automotive. So in our company, we are using Hypermesh, ANSYS, and Primer. So these softwares will be used for the pre-processing. So once the pre-processing done by using these softwares, then we will be need to submit the runs in the solver. So the solver here, we are mostly using ANSYS, ABAQUS, NASTRON, LS Dyna, and PAMCrash. So that ANSYS, ABAQUS mostly we'll be using for the linear calculations, means for the durability cases, and for NVH cases, we'll be using mostly ANSYS, ABAQUS, NASTRON. When it comes to the crash, so we'll be using the LS Dyna and the PAMCrash. So once the results we are getting from the solver, we will be doing the post-processing in Hypergraph, Hyperview, or Animator. Sometimes we'll do in Patron also. So next we move on to the automobile safety. So the automobile safety is the study and the practice of design, construction, equipment, and regulation to minimize the occurrence and consequences of the automobile incident. So the reason why we are going for entire study, that end of the day, that we should avoid the accident, or in case if the accident is not able to avoid, at least we should protect the occupant. So for that we need a few systems. So in that we have called active safety and passive safety. So in that active phase safety, so it helps us to avoid the occurrence of crash. So it will prevent the crash. So it will try to avoid the crash. So for that we have different systems are there. Those are anti-locking braking system, electronically stability control, and we have that mirrors, adaptive lighting system, seat belt reminder, lane departures. The another one is called passive safety. So in case if accident happened, so during the crash time, so it will protect the occupant. Okay, it will protect by airbag or that energy absorbing brackets or collapsible steering column or pedestrian protection system, seat belts, anti-intrusion bars, crumple zones. So these are the systems that will help to protect the occupant. Yeah, the next we'll move into the crash worthiness. So what is the crash worthiness? The crash worthiness is the ability of the vehicle to protect its occupant. So that is called crash worthiness. So how we can achieve this one? So this can be achieved by the various methods are there. So by crash energy dissipation, okay, efficient dissipation of the crash energy by controlled vehicle deformation. So by this method we can control, and we can control through the passenger compartment integrity and controlled crash deformation pulse. So exactly what it means. So once the crash happen, so the energy will transfer from bumper to the passenger compartment. It will transfer through the bumper, front frame, and crash cam through many parts, that all the energy will transfer to the passenger compartment. The thing is here to avoid any injury to the occupant. So most of energy should be absorbed in these areas only, either bumper or crash can or front frame. It should absorb the more energy. So when it reaches to the passenger compartment, the energy level will be very less. So if energy level is very less, so the occupant will feel very less acceleration. So different types of the crash. So first is the frontal crash. The frontal crash, here we have again some more types are there. Full frontal rigid barrier and offset deformable barrier and small overlap rigid barrier and oblique impact. So these cases are coming under the frontal types. And next is the side crash types. In side crash, side rigid pole and side deformable barrier. So these are the two types of the crash inside. And when it comes to the rear crash types, full rigid barrier and rear deformable barrier. When they come to the roof crash, roll over. The pedestrian protection, we have lower leg, upper leg, and child head form and adult head form. So we have different types of the crash simulations are there. So these simulations will be performed based on the regulations which is given by the government. So one is we need to perform all the simulations as per the regulations, and we need to perform all the simulations as per the requirement of the each customer. Maybe if they ask to perform as per the NCAP, we need to perform simulation as per the NCAP also. Actually, this regulation is controlled by, framed by, and controlled by the government, and the NCAP is the private body. For example, whatever slide, just I'm showing only one slide for this regulations, and I'm not showing anything for the NCAP, since our interest is mostly on the HBM. So first we will only go through slightly about all the regulations, then we'll move on the human body modeling and analysis. So here, if you take the crash regulations, this regulations is for Europe, United Nations, USA, China, and India. So in previous regulations, India will not be there most of times and most of places. Now in the new regulations, you can see India also in the regulations. So for each and every assembly or sub-assembly, so we have certain regulations are there. So we need to make that part or a sub-assembly as per that regulation, and as per that regulation testing procedure, we need to perform the analysis. Then once get completed the analysis response should fit within the limit of the criteria which is in the regulations or NCAP. For example, if we take the frontal impact, so for UN, we need to have the regulation called R12, R14, R16. And for US, we have FMVSS. And we have for same way, India also, we have IS 15139. So like for different impact or different part of the car, we have the regulation. So as per the regulations, we need to build the part, and then based on the testing procedure, we need to perform the simulations, and whatever the results we are getting from the simulations, that should be within the limit of the criteria. So in the next slide, just only I am showing the FMVSS 208. This is for the frontal impact requirement. So in the frontal impact requirement, this is for US. So we have two different conditions are there. The one is the unbelted. So passenger or occupant will not wear any belt. So this is unbelted mode. Another one is the belted mode. This is in the full width test. So example, if you see, have a look on this picture. So this is a full width test. You have the full barrier is there. So your car having full contact with the barrier. And here in the seat, we have placed the dummies, hybrid 3 5%. Hybrid 3 5% means this is a AF05, adult female dummy. So here for passenger side and driver side, in this case, we have kept two female dummy and we will perform the test. So then the same way we will perform the simulation also. Then we need to correlate the simulation test with our with the physical test. So if the results are matching, it's okay, well and good. In case if does not match, again we need to go for different kind of iteration on the simulation model, and we try to achieve this one. So the same way they have for 50% male dummy also. The 50% male dummy here, in the 50% female dummy unbelted mode, the speed is 30 to 40 km. Here also they are giving 30 to 40 km, but it is an angular shape. So it is not the direct full width impact, this is angular impact. In the angular impact, they are keeping hybrid 3, 50% dummy in driver and passenger side. So the belted mode also, we can see what is the speed. So in that unbelted mode, the speed is 30 to 40 km per hour. In belted mode, it is 56 km hours. When it's come to the ODB, offset deformal test, here the speed is only 40 km per hour. But it will have the contact only the 40% of the car, the barrier. So the most of energy, it will be transferred only this region of the car. So the injury of the severity level of the injury will be high in these cases. Yeah. So next we'll move on to the dummies. Okay. So to evaluate the injury level, okay, to assess the kinematics of the occupant, so we are using some devices called ATT. So it is called anthropomorphic test device. So this will replace the human inside the car. So this dummy, so it will be developed based on the human size, weight proportions and articulation of the human body during the collision. Okay. So these dummies are used by the researchers and the automobile and aircraft manufacturers to predict the injury person to might sustain in the crash. So modern dummies are usually instrumented to record data such as velocity of the impact, crushing force, bending, folding, torque of the body, deceleration rates during the collision. So before we are using that crash dummy, so that time we will be using that the testing is done by using the human cadavers or animals and live orienters. But for using the human cadavers, since we need to perform more number of testing, getting the human cadavers is very difficult, and we have so many rules and regulations are there. And animals, nowadays we have so many rules, so as per that we cannot use any animals for the crash test. So now the only option is now we need to use for the dummy. So we will see how the dummy evaluation is there. The first dummy they developed in 1947, that is called FE3A. So this dummy is developed not for the automotive, this is developed for the aircraft. The same time they developed another dummy called FE3A also. In 1950, first they developed VIP 50 series dummy. So this dummy specifically for General Motors and Ford. In 1981, so that performance of that means the response of the VIP 50 series dummy is not as per expectation. So what the GM engineers has done in 1971, so they combined FE3A and VIP 50 series, best features of these two, and they created the new dummy called Hybrid 1. So the first they created Hybrid 1 dummy, that is for 50 percentile male, means it will be called as a AM 50 percentile, means adult male 50 percentile. So again in 1972, from the Hybrid 1, they developed another dummy called Hybrid 2. So the Hybrid 2, so here we can see the better response compared to all other series. So we can get better response than FE3A, VIP 50 series and Hybrid 1. So in this Hybrid 2, so they improved the shoulder, spine and the knee responses. But still we have done some improvement on Hybrid 2 also. Still the Hybrid 1 and Hybrid 2 was very crude, and there was limited to developing and testing the seat belt designs. So these two dummies is not compatible with the seat belt designs. So again from this they moved into the new dummy that is called Hybrid 3 family. So this they developed in 1976. From 1976, still we are using this dummy for few cases as per the regulations. So in that in Hybrid 3 family, first they developed 50 percentile dummy. So 50 percentile dummy means AM 50 percentile adult male. So it has the height is 175 centimeter and the mass of that dummy is 77 kg. And the next is they developed 95 percentile Hybrid 3 dummy. Here the height is 188 centimeter. It's compared to 50% is more, and the weight is 100 kg. So these two are the male dummies. 50 percentile and 95 percentile are the male dummy. And next they created the new dummy, fifth percentile female dummy. So here the height of the female dummy is 152 and the mass is 50 kg. Actually, only the hybrid people, they created only 3 dummies for the entire population of the world. So they have only AF05 only for female, and for male they have AM50 and AM95. So they have done some survey the entire world. So based on the survey, they're using standard deviation and other stuffs, and they arrived with these dimensions, means this height and this mass. Same the hybrid family, they are having the child dummy also. The child dummy is for the 10 years old and 6 years old and 3 years old. So while doing the calculations and simulations, so we need to keep all the child dummies in the rear seat. So this is all about the hybrid family. Next, there is another improvement is there from the hybrid 3 family to another improvement called dummy called THAR. This is THAR means this is a test device for human occupant restraint. So it's advanced 50 percentile male dummy. So already we have 50 percentile dummy, but it is also advanced. How it advanced means it has more number of sensors are there, and it can calculate accurately all the deflections and other forces. Why? Because in the hybrid 3 dummy, the most of parts they used as a rigid part. So wherever we need to measure at that locations, they will keep some either accelerometer, they will need some sensor, they will keep a load sensor, or they will use some potentiometer to measure the response of the dummy during the crash. But here in TAR, we can keep more number of sensors, more number of accelerometers, potentiometer, and they converted a few parts from the rigid part to converted as their flexible parts. So that response will be almost, it will be better than the hybrid dummy, hybrid 3 family. Okay, still at present in the market, they are using hybrid 3 family and TAR models. Okay, but whatever till now we discussed, this hybrid 3 designed one research effect for only for the frontal impacts. So, but we have seen that while seeing that different type of the impacts. So we have side impact is there, we have rear impact, like that different impacts are there. But whatever till now we have seen, that is only for the frontal impact. So when it comes to the side impact, so for side impact we have different dummies. So whatever we are using for the frontal impact, those dummies cannot be used in for the side dummies or rear impact dummy. So when it comes to the side impact dummies, they are using SID. So this SID is only for the United States government testing standard. So if you are performing cross test as per this US government testing standard, you have to use for the SID. In case you are performing the simulation or physical test for the Europe, then we need to use for the Euro SID. And in case if you are using for the female, the first two is for the male. If you are using for the female, so you need to use for the SID 2. So these 3 dummies are used for the side impact. When it comes to the rear impact, so they are using dummy called BioRead. So this dummy will be used for the rear impact. And for the rear impact, they developed the new dummy called also CRABI. So the CRABI child dummy, it is for 18-month, 12-month, 6-month old also. When come to the hybrid family, we have only for 10 years old, 6 years old, and 3 years old. But in a rear impact dummy, we have means CRABI, we are having 18 months, 12 months, and 6 months old dummy also available. And they developed a first generation O-based anthropometric test device also they developed in this. But this FGOA we are not using at present. So these are about the dummy. Human will behave the same way the person with the device will behave. Yeah. And this is the hybrid 3 family dummy. So this is hybrid 350 percentile dummy technologies. So here, so this is the FE model of the device. Means the FE model as a ATT. The ATT will be used for the physical test. Then the same shape and the size, everything they developed in as a FE model. In the FE model, this will be used in our crash simulations. So here, if you notice here, so here we have the head CG accelerometer is there. Here neck and movement we have force and sensors are there. Here we have one more sensor to measure the chest deflection or sternum deflection. And here they keep one more accelerometer. Here means in thorax region. This is pelvis region. This is the force sensor at the femur regions. Femur for the right side and left side. And how much the knee is getting slide. For that they will be having one sensor here. And the same way, this is for the lower extremity. The lower extremity has the upper tibia sensor and lower tibia sensor. So in hybrid 3 model, so majorly this kind of sensors will be there. And accelerometer, potentiometer, load cells will be there. So by using this one during the physical test, it will record all the output. Yeah. So now we saw this one, and this is for head. So head. So from head, what we can measure? So from head, we can measure what is the resultant acceleration and what is the head injury criteria value and acceleration value for the 3 millisecond clip. The maximum peak when we are getting the acceleration at this location, we need to measure 3 millisecond clip for this one. So we can measure these things from the head sensor, head accelerometer. And when it comes to neck, so from the neck we can see, we can measure what is the bending moment and tension force, shear force and neck index. So these kind of things we can measure from the this sensor. from the chest sensor, from here we can measure what is the resultant acceleration and what is the deflection, chest deflection and chest deflection viscous criteria. So these things will be measured. And same way, when it comes to the pelvis region will measure what is the pelvis acceleration and what is the pelvis displacement. Those things we can measure here. And by using that femur sensor, we can left side and right side how much force it is getting experienced. And during the crash, what is the sliding happening on the knee. And by using these two sensors, and upper tibia and lower tibia sensor, we can measure what is the force and we can measure what is the movement is happening at these locations. And when come to the neck, so neck we have again different kind of things as happening. So neck, during that our simulation, neck you can go for tension mode or compression, or we can experience some shear, and it can measure moment forward flexion and moment backward extension. So these three things, all will be recorded in the sensors during the crash simulation, physical crash simulations. Okay, so this is at the knee location, and the knee location we can measure what is the force, knee force. So during that crash, the knee will go and impact with the IP. So it will experience some force from the IP. So that force we can measure here, and there is a possibility of the sliding of the knee against the IP. So those things we can measure here. Displacement also we can measure. And we can measure the tibia index. So the tibia index means it's nothing but how much we're getting the force, FZ. And from the floor, how much force you are getting and how much your heel is rotating. Means what is the moment based on the moment and that force, and we can calculate something called tibia index. So these are all the major injury criteria points. So these points we need to measure from our test simulation, and then while doing the crash by using the FEM, then we need to compare whether we are getting the same as or not. In case we are not getting, then we need to fine tune the model. Means fine tune the model means we cannot fine tune the dummy, we need to fine tune the structural parts. Yeah, it will be, this is that FE model of the hybrid 3 dummy. Yeah. So these are all the points is given in the NCAP. So now we discussed what will be measured in that our physical simulation and what will be measured in that our crash simulation. But those after, even though measuring and comparing with that, whatever you are getting the value, that should be lesser than this given value in the regulation or NCAP. For example, if you see that this is for occupant injury ECE R94 regulations, this is for Europe country. So here you should not get your HISP value more than 1000. If you get that more than 1000, so you will not be getting the star rating for this. The same way for the neck tension also. So the neck tension, there means initially it should be 3.3 kilonewton at 0 millisecond, and 35 millisecond it should be 2.9, and for above 60 millisecond it should be 1.1 should be there. So these all things we need to measure, and we need to cross check whether at this millisecond what is the force, at this millisecond what is the force. In case we are getting the more force, means we need to study and we need to understand why we are getting the more force, and we should reduce that force. The same way we should check for the neck shear also. And thorax compression, they said that it should be less than 50 millimeter, and viscous criteria 1.0 meter per second. When it comes to the femur force, it should be around 7.58 kilonewton more than 10 millisecond. Means more than 10 millisecond means at the time your leg will be contacting with the IP, so it will experience some forces. And the knee displacement should be less than 15%. And the DPR compression force is 8 kilonewton and tibia index 1.3. So this is for the occupant injury ECE R94 given by the Europe government. And same way we have for that NCAP also for Europe. So here still we have in details will be there. So based on that your value, your points will be changing. So based on these points, your rating will be get reduced. If in case we are getting good amount of points, then you will get more points. In case your points is very less, then the rating will be less. So this is for IIHS, Institute of Highway Safety. So here also they are given the rating. So as per this rating, here you should, this is for US, here you should get HIC, injury criteria, should be less than 560. And NIJ should be less than 0.8. So actual tension and should be less than 2.6. So we need to meet all the criteria for neck, chest, and legs and feet. So these are the dummy families actually what will be available in the market right now, and which is used for the simulations. And right now, as I said earlier, now we are using mostly hybrid 3 5% dummy. So the weight of this dummy is 49.1 kg. And when it comes to the 50%, it is 77, and 19.5% means it is around 101. So the advanced version of the hybrid 3 dummy is that TAR 50%. So this is 76.7 kg. But if compared to this one, the TAR dummy is 1 kg is lesser. The same way also we have the tabulation is there for the side impact dummies also. And we have the child dummies also. In the child dummy, now mostly are using the hybrid 3 years, hybrid 3 6 years, hybrid 3 10 years. So the 3 years means 16 kg and 23 kg for 6 years, for 35 kg for the 10 years. So these are the dummy you are using for the hybrid family. So next we'll move to the TAR. So till now we have seen only the hybrid. So now we are going to see the TAR dummy. And as I shared earlier, that we can measure more number of responses in the TAR, and it has the more flexibility also. So we are using the TAR dummy also based on the regulations or the NCAP. So here what we will be doing here. So this is the TAR dummy. This is the physical dummy. So in the physical dummy, so same way we have the FEAA also for our crash simulation. And the physical dummy, they will have some certification procedure will be there. So as per the certification procedure, first we need to develop our FEAA model, and then FEAA model we need to perform more number of iterations or simulations. Then that simulation response should match with the experimental or the test procedure whatever they done. As per that what they got the response, the both should match. So that is that challenging for here. For example, in case if I am going for component test, this is for the neck. For the neck, we need to perform. So neck is coming in the upper body test. We need to perform neck torsion, neck flexion, neck extension, neck lateral. So for these 4 cases, we need to perform in our FEA simulation. But already these things they performed for the physical test. So the physical test they have, and we have that response of the physical test. So based on that, we need to modify this part. Means we cannot change the shape of the part, but we are allowed to change the material parameters and material behavior. So by changing this parameter, in case if I am doing for the neck torsion, so I should have the lower, I have the lower limit 36.1 Newton meter and upper limit is 39. So in order to achieve this one, I need to change the material property or material characteristics of this one, and I need to perform, and we need to achieve within this range. In case once I achieved for the neck torsion in component level, then this for same neck we need to perform the flexion also. Okay, so in order to while performing the flexion, in order to achieve this limit, we need to again modify the same part or some different part material property or characteristics. So if while performing or modifying those things, that should not disturb the neck torsion results. In case again disturbing the neck torsion, so again we need to find the common way to perform, or what is the common part or material which is affecting these results. Those part only we need to check it, and those part again we need to perform the simulation, and we should get the our response within this limit. The same way we have to do for neck extension and neck lateral also. So this is all only for the neck, and we need to do for component level for the lower leg also. In the lower leg, we need to perform the knee. So here knee, we need to perform what is the force is experiencing and how much the slide is there. So these things we need to perform. The same way, once we completed that component level test, when we need to incorporate all that whatever property or characteristics we achieved, that we need to incorporate in that full model, and again we need to go for the full body test. The full body test, here we have to go for first one is the head impact and the face impact. Here we can see the picture. Another one is that we can see the upper thorax, and we need to perform for the lower thorax and abdomen also. So, and this is for the lower leg. So as per the certification, we need to perform n number of iterations, and finally we need to make a perfect model, a FEA model. So once we made the perfect FEA model, so whatever that response you are getting from the FEA model, it should match with the physical test. Once we are achieving that one, then we can keep these dummies in the car during the crash. So before keeping the dummy in the crash, we need to do this many iterations and calculations for that. So this is for Thor dummy, means the test device for human acupuncture system. So next we'll move on to the human body modeling and analysis. Just a moment. Hello? Yeah, okay, thank you. Yeah, now we'll move into the human body modeling. So this human body is called thumbs. This is total human model for the safety. So as I told previously, in hybrid 3 family or the Thor family, we'll have more number of rigid parts will be there, and that deformer parts will be very less. And when it comes to that human body modeling, so we have that model just as per the human. Whatever the parts are human are having, the same parts will be available in the model. So this one, the thumbs is a virtual human body models or program for computer analysis human body injuries caused in the vehicle collisions. Compared to the physical crash dummies commonly used vehicle collision test, thumbs is able to analyze the collision and related injuries more detailed because it is precisely model the shapes and durability of the durability of human bodies. And 2021, the Toyota has released this dummies, this thumbs model available, means freely available in their website. So if we need this model, we can log in, register in their website, and we can get all these models. And here they explained what is the evaluation of the thumbs. So this is the first version what they developed. This is the whole model, and in this model only they developed the internal parts in the version 1. Actually, the past 20 years, the Toyota guys are working in development of a thumbs model. So almost now they are in the version 6 after 20 years. In the version 2, they modeled the detailed face. And the version 3, they modeled the detailed brains. So we have whatever brains are there, the cerebellum, other stuffs are all there, that all they modeled here, and all the skulls all is there. And in the version 4, they included internal parts and detailed inner organs. So here in that model, we have kidneys will be there, liver, heart, lungs, all spleen, and all the things are available in the model. So the next, they included muscles, and now muscles and organs, again, they updated these things. So if see this model, it will be like the real human. So the real human, we have the head. What are the parts are the inside the head? It will be the most of parts. And here we have this is a upper extremity, means this is a upper arm and lower arm. The upper arm we have the humerus, and lower arm we have the radial and ulna, and the wrist also it is modeled as per the human. So the entire organ system also it is available. Even you can see inside the artery, veins, everything it is there in this model, in the thumbs. So these models, what are you seeing at this left side, this model is used for the pedestrian models. So as I mentioned earlier, this is used for the upper leg, lower leg, or child head impact and adult head impact. We are using these models for that. When coming to occupant, so occupant models, these are the models. This is for 3 years, 6 years, 10 years, and adult female 5 percentile, adult male 50 percentile, and adults male 95%. So these are all the models available in that website. So if you're really interested on that, you can register in the website, you can download, you can have a look. So these models are used to predict the injury and correlating that test simulation with FEA. So now we'll see the few projects what we carried out for the means by what we carried out by using the thumbs model. So in that the first project is that effect of seated posture on vertebral compression fractures in frontal crash using the HBMs. So in that objective of this project is we need to study the vertebral column and over vertebral column under the dynamic loading condition. So this is the objective of this project. So when it comes to going to study about the vertebral column, so first we should have that knowledge about the vertebral, what is vertebral column, how it functioning, how the other parts are there. So once we got this kind of project, then we need to detailedly study about the anatomy. So this is the anatomy of the vertebra. So actually the vertebra having 33 individual bones will be there, and that's interlocked with each other to form the spinal column. So these all the vertebrae, whatever vertebrae are there, the 33 vertebrae, it is making is forming the final column. And the vertebra is based on the location and based on its the function, it is having the different naming is there. So for example, if you take this condition, this is cervical vertebra. So in this vertical vertebra, it will support for the head. So it is having total 7 number of vertebra from C1 to C7. The next one is the thorax. So the thorax, the function of the thorax spine is, or thorax vertebra is to hold the rib cage. So we have the rib cage here, and inside that we have the heart and lungs are there. So protect that one. This is the function of protecting the rib cage and protecting the heart and lungs. So that is the function of the thorax. And another one is the lumbar. So this lumbar is the function, main function is it has to bear the weight of entire body. So but cervical, it's only that responsible for that head, and thorax, it is only responsible for the rib cage and heart and lungs. And but the lumbar, it is responsible for the entire weight of the human body. So and it is having total 5 number of vertebrae are there. It's number L1 to L5, and these vertebrae are much larger in size to absorb the stress of lifting and carrying the heavy objects. So the size compared to all other cases, I mean other vertebra, the lumbar vertebra will be more. And again, we have 2 more vertebral columns are there. One is sacrum and another one is the cox region. So the sacrum and the cox region are the fused one, so it will not movable. But rest the cervical spine and the thorax spine and the lumbar spine are the movable one. Since the size of the lumbar spine is the size bigger and it has to the more load, so first we have started our analysis from this part. So we have taken that L2, means next to the L1. The L2 we have taken the vertebra. So this is the shape of the vertebra. In this vertebra shape, this is the body, and this is that vertebral arch, and this is some process attachment. And here the load transferring path is only on the body. So since only our area of interest on the body, only we have taken this part for a simulation, and we cut the other arch and other process things. We removed that one from the simulations. So first we have taken this part. So for this we have some research paper already available in that particular websites. So on the websites we need to pay some time money or we can get it. So as per that research paper, we need to first fix what is the boundary condition of this one, the simulation, and what will be the velocity, what is the input, load input. So those things we need to take from the research papers. So for example, for this case, so they have one fixed plate, some rigid plate will be there. On that they kept some foam parts. Above that we keeping the vertebra. The same way top also on foam part, and again rigid plate, and again the load will be applied from the top. So this is the test condition, boundary conditions which we have taken from the technical paper. Then we simulated this one. Then when we get the response of this simulation, this response should match with the technical paper what response they got based on their physical test. So until getting the test response, so we need to modify the material property, or we need to modify the characteristics of the vertebra body, and we need to perform the iteration, and finally we have to match that one. So once we matched this one, this is only we have done only for the single vertebra. So then we need to go for the multiple vertebra parts. So again we found some other papers. This is different loading condition and different setup. So based on this setup, again we need to perform the iteration. And here already, as we fixed the material and characteristics for the vertebra, we will not disturb anything on that one. So instead of the vertebral body, so we will be disturbing the something called nucleus will be there, annulus will be there, and disc. So other properties are there. So other properties we need to disturb, and we need to achieve, means we need to correlate the simulation results with the test results. So once this is achieved, then this model we will keep in our full vehicle simulation. So this is full vehicle simulation. This is the cut model. We will not use the entire model. If we use the entire model, it will take more number of time to do the matrix calculation. So we'll take the cut model only for simulations. So once we keep once we achieved the material property for all the vertebra and other parts, annulus, nucleus, and disc, so that will incorporate in that model, and we'll do the simulation. And this simulation here we can see this is at 0 millisecond. So then once the crash started, means that the simulation started, or during the crash, what will happen, that the dummy model, means the thumbs model, the head of the means the human try to move forward during the crash. So once the human trying to move forward, so based on the sensors, the airbag will start open, and we have something called seat belt also. The seat belt we have retentioner and we have load limiter as there. Once the crash happen, the sensors will experience that there is sudden deceleration happening in the car, the vehicle. So if any sudden deceleration happening with a particular millisecond, then automatically this airbag will get open, and this pretensioner and load limiter, everything start to react. So this airbag and the pretensioner, load limiters, all is coming in the passive safety. So what's happening here? So during, once that crash occurred, that entire body is trying to come forward. So the head will try to come forward, and at the same time that airbag should open. So there is some relationship is there between our airbag where it placed. It means the distance between airbag and the human head. So within some 20 millisecond, airbag also should open and head also should go, and it have contact with the airbag. So the injury of the head will be reduced. Else what will happen, that head directly will impact on the steering column. So it will experience more acceleration. So then it will, in case if it crosses the limit, then it will not be approved by the regulations or NCAP. Still, if it crosses, then it will, the occupant also will get the injury. The occupant may die also due to the more acceleration. So that will be prevented by the airbag and a seat belt. Okay, and the same time we can see the chest also is going to contact with the steering. So this here we need to measure how much the head, chest is getting deflected. So if it goes beyond certain limit, then it will not be passed, and the human also will get injured. The same way we need to here see what is the pelvis, how much it is experiencing the force and how acceleration and how much pelvis is moving forward. So in case pelvis is moving more forward direction, that our knee, it will go impact with the IP. So in case it's go impacting with IP with huge velocity, so you will get the injury for the knee also. And based on this kinematics of the occupant, the foot level also will change. The places of the foot with a turn time to try to rotate, and it will go, come to, it will slide on the floor also. So this, all those things we need to check once we are submitting the full run, and in each locations we need to measure what is the output we are getting from here, what is output responses. And in this case especially we are checking about the vertebra. So we here measured what is the force we are getting in the vertebra and how much that movement is happening at these locations. So this entire study has been done for this project. Excuse me, hello? Hello? So can I take a few more minutes, or is it okay, boss? Okay, fine. Okay, thank you. So why? Because now we are changing that, means why we are studying on the vertebra. This, the vertebra is the, based on this vertebra, that the posture of the spine is will be changed. So here we can see different kind of the posture. So if this one is called DK, means thoracic kyphosis. So here from T5 to T12, the shape how it will be the spine, and the lumbar lordosis is there. This is L1 to L5. So based on the posture, so that how much is force is get experienced by the vertebra and how much the moment is, that will be different based on the postures. So that's the reason we need to study about the postures. So the next one is that project is influence factor on the seat belt kinematics during the collision. So how the seat belt kinematics is there during the collision, and what are all the factors are influencing for the seat belt sliding. For this study, so the objective of this project is to study the effect of the lap seat belt engagement relative to the pelvis. So what are all the parts going to influencing the seat belt movement? Means here it is called as lap belt, not seat belt here. So the lap belt. So the following factor influencing on the pelvis orientation. One is the pelvic angle, another one is the pelvis shape and the pelvis size, and initial relative position between ASIS and the lap belt. So these are the locations. So these are the images we taken from the hospital. So we have the tie-up, means the client having some tie-up with some hospital. From the hospital they are having this kind of pictures, and based on the pictures we will modify the pelvis. So this is the pelvis. So, and what is the first shape point is, so we need to study about the pelvis angle. The pelvis angle means angle between anterior superior iliac spine to pubic symphysis. So between the angle means this is one ASIS and this is the PS. What is the angle? So this model we can scale the model, or we can scale up or scale down the model. So by the method we can get n number of models. So based on the model we need to perform the simulations. So this is one example for the ASIS. The same way we can change the pelvic shape also and the pelvic size also. So after that we need to perform that simulations. In the simulations, the what are that parameters means pelvic angle, pelvic shape, and pelvic size, and flesh thickness. So based on that changes. So we have that responses from the simulation, and simulations mostly will be measuring the lab belt sliding Z direction, how the lab belt is moving up. Okay, I think here we can go. This is the lab belt. This is the lab belt based on that shape or angle, some other parameter, how much is sliding moving upside. That we need to measure. Why? Because if the slide is in that lab belt is sliding more, it will go and compress the abdomen. So at this region, if compressing happening here, the pelvic bones are there, it can withstand the more load. Once it comes to the internal organ, it will damage the internal organs. So that is the reason why we are studying for this task, and not only for the belt force, and we need to study what is the rotation of the pelvis, how much it is rotating, how much angle based on the psi part change, and how much it is moving in the X direction. So this study has been done here, and we came for the conclusion. For this, we have to do something statistical study, and the statistical study we need to prepare some 10 percentile and 50 percentile and 90 percentile models. As per that model size, we will do the simulation and we will get the output. Yeah. And the next one is that obese model. So obese occupant, nowadays the people, you can see more people are in the obese condition. So the obese conditions, because of the obese conditions, frequently suffer from the submarine injuries. Submarine injury means that, so because of the obese, the seat belt will not fit properly on that lap. So it will try to come towards the chest side. So if it comes towards the chest side, so it will disturb, means it will hurt all the inner organs which are there and that locations. So for that we have done some couple of studies. So first we have done some for the frontal cases. Frontal cases we have taken AM50, means adult male 50 model. So first only we changed the chest. The chest we scaled up in the X direction. So we scaled up 1.05, 1.1, 1.3 as per the requirement, and we studied what is the effect. Same way we scaled up the thigh model also, only the thigh. The thigh means in Z direction we scaled up, and we studied what is the kinematics. So same we have done for the side crash also. From that we came to the conclusion, okay, if the person is like that, we will get this much injury. Person is like that, we will get this injury. This is all about the human, means male model. So vertebra we done in the male model, and this is seat belt kinematics, and this is obese also in male model. So another interesting thing is this is that pregnant occupant. So this we cannot do in that hybrid, and we cannot do in the Thor model. So this we had done in that the thumbs model. So here we have already female model is there for our thumbs. So we have taken this AF05 model is there. By taking this AF model, here we incorporated some more parts called uterus, placenta, and fetus. So these all we kept modeled, and that is placed inside that human, and the simulation has been done. So based on that, so almost this will take for the 9 months baby. 9 months means around 36 weeks baby we will consider. So that dimensions and all everything we can collect from the hospital. From the hospital dimensions we can create the model ourselves, and we can incorporate in the existing dummy, and we can perform the simulations. And here to that check whether that during that, means at around 9 months, if you have some any crash happening with 50 kilometers per hour or 45 kilometers per hour, that the child will die or not. What is the fertility? That we will check it in this one. So that here we will check based on the strain on the uterus, something called UPI, uterus placenta interface will be there. That should not tear out. If it start tear out, the baby will die. So that we will check it in these cases. And till now whatever seen, this is for the entire model. And now just some compound level also we will be doing. For example, we will be doing for that lungs also, how much forces, livers, spleen, and large intestine. So like this we have done for all the cases. Even for uterus also we have done separately the specimen level simulations also. And for bones we have done. And since we need to do many number of iteration in order to match with our FEAAA results with the test results, so we introduced the ML technique. So using the machine learning techniques to match, means to reduce the number of iterations. So in case if it takes if doing manually, if it takes some 3-4 days, in case if we're using ML, we can do it within 1 day. Now we introduced this also to the organ level, means part level, we can do by using the machine learning technologies. Yeah. Yeah, that's all from my side. Is any questions are there? Hello. So yes.
Sir, can I speak, sir?
Yeah.
Sir, thank you for giving very fine illustrations.
Thank you.
Sir, when you have arrived at the belt positions, or say rather, you have got the data from the hospital, the clinical data, and use it for the design purpose. You have, so, you have principally concentrated on the bone strength and other properties. Can I take it like that, sir?
Actually, I think I told in different way. So the belt position will not take from the hospital. We will take from hospital what is the pelvic angle and what is the pelvic shape and what is the pelvis size. So these and all will take from the hospital. Okay. From as per the dimensions, we will create the FE model. Then on that, we will make the resistance system lab belt. Based on this pelvic angle or pelvis size or pelvis shape, how that lab belt kinematics getting changed.
Okay.
Okay. So in case if the seat belt lab belt is coming more towards the chest direction, okay. So what will happen from the pelvic? Pelvic, we have more number of bones are there. So even it can give more number of force to pelvis, there will not be any issues. But it comes to the abdomen, so there we have more number of internal organs are there. So during the compression, so it will hurt, means it will make damage on the organs.
Okay.
Yeah.
Sir, are you going to reconstruct the skeletal structure and apply load, sir? How should I think it in that way?
Yes. So already we have that base model from the Toyota.
Okay.
In the Toyota model, again we'll remodel that one based on the available data, and that we'll be using for the simulations.
So, thank you, sir.
Thank you.
It's clear.
Thank you. Actually, the time is very short, so that's the reason. Just I was in hurry, means I could not talk more also. So, yeah. For at present, all the OEMs they're preferring for ANSYS rather than hypermesh. Yeah.
Sir, I missed a few minutes. Can I be made clear that you are going to make the analysis using which software?
Analysis for this kind of crash and simulations, we are using LS Dyna.
LS Dyna. Okay.
Yeah.
That's right, sir. Thank you, sir. Thank you.
Thank you. Thank you. Yeah, thank you. In case if I have any queries, you can contact me later also. Thank you. Thank you all. Yeah. Thank you.